Okay, so question number one, we are given this block diagram uh, here, and we have been asked to find out an equivalent representation by moving this delay block to the right. So we have to move it to the other end, right? So to solve this problem, it's quite straightforward. All we have basically this problem is to show how we can use the noble identities that were discussed in one of the lectures, where so there are two noble identities. One is that whenever we have some downsampling block followed by some any filter h of z, then we can replace these two blocks, let's say like this. This is some other filter h1z, and the downsampling block is moved to the right. Now these two block diagrams will be equivalent when this h1z is equal to h z raised to the power m. So then we can say that these two are equivalent. There was another result where we had an upsampler of a rate L. So in this case, when we have this h of z and L, so when we want to replace it like this, we want to move L to this side and h of z here. Then if this is some h1z which is equal to h z raised to the power L, then we can say that the two block diagram representations are equivalent. So using these two, we will solve this question. We will first let us look at this originally the block diagram that was given in the question. First of all, let us try to interchange these two blocks. So this is a downsampler of 2. So when I move it to this side, what will happen is that it will become z minus 2 raised to the power 2. So that is basically z raised to the power minus 1. Now we can also exchange these two blocks. There is an upsampler, and in this case, what will happen is that again it will be raised to the power of 3. So when we move it to the right, we get z raised to the power minus 3, and this is the final block diagram. So what we can say is that this one is equivalent to this one. So this is it. It was quite straightforward. We just had to utilize these noble identities. And using these noble identities, we can actually obtain a lot of interesting results. Okay, in the second part, we have been given this system. This is the second question. We have been given two different ways with which we can cascade a decimator, which is this of of a period of with a value of d, and an interpolator which has a value of I. So there are two ways in which we can arrange them in a cascaded manner, either by A or by B. In A, we have interpolator first, and in B, we have the decimator first. So now this question says that if D is equal to I, so now since D and I are nothing but the integer values, if we take them to be equal, we have to show that these two output configurations are different. Or in other terms, y1n is not the same as y2n. And therefore, these two systems are not identical in general. So let's first do this part before we go to the second part. So let's say this is the signal x of n, which is the input sequence. So x of n is basically made out of these sequences x naught up till x of n. X of x of n. So when we take d is equal to I is equal to 2. First of all, when we pass a signal through decimeter, recall that what happens is that it will only take the values corresponding to whatever its value is. So if it was d is equal to 3, we would have gotten it would have selected every third value. In this case, it will select every second value. So when d is equal to 2 and we pass this x of n through this d, what happens is we will get x0, x2, x4, and so on. So using this, so we'll first look at the case when there is a decimator first. Okay, yeah. So first look at the case when there is a decimator first and then an interpolator. So let's call the signal z2n. Xn was x0, x1, x2, and so on. Z2 is basically every other value of that sequence. So it is x0, x2, x4, and so on, because the value of D is 2. Then we pass this signal through this interpolator, and what this interpolator will do is it will move these signals by a value of 2, because I is equal to 2. So which means that there will be a single zero that is inserted between every value of z to n. So it will be x0, then a 0, and then x2 and 0, and so on. And this is what y to n will be. Similarly, let's look at the interpolator first case. And in this case, what will happen is, because there is an interpolator first, so whatever the signal x of n is, it was x0, x1, x2, and so on. There will be 0 inserted because I is equal to 2. So there will be a single 0 that is inserted between every value of the sequence. And when that is how we get z1n, again we pass it through the decimator, which will select every alternate value. And when we do this, so basically we get the original signal x of n, because the zeros will be eliminated, and we will get x0, x1, x2, and so on. So y1n is nothing but xn only. So you can see that y1n and y2n are not same. And basically, uh, just a second. Yeah. Okay, so basically that goes on to show that both the signals, uh, that for D is equal to I is equal to 2, both these block diagrams are not the same. So that is the first part. Are there any doubts so far? Also, am I clearly audible?
Yes, sir.
Okay. Okay, then I'll continue. Let's look at the second part of this question. Now it is asked uh, for us to show that the two systems, that is A and B, are identical if and only if D and I are relatively prime. So basically, D and I are relatively prime, which means that they only have a single, they are only divisible by 1, both of them. So let's look at this part. So let us take some generic D and some generic I. We have taken D, which is some value D, and multiplied with K, and K is some common factor. Similarly, I is taken as some small I and multiplied with K. Now this K could be any value. It can be any common factor, and if they are relatively prime, it just means that D is equal to small d and I is equal to small I, because we have selected these D and I to be relatively prime. But if K is not equal to 1, then these two numbers are not relatively prime. So let's take this case. We again have this input sequence x of n made out of these entries. We take the case of decimation first again. So here, if we have decimation first, we first of all obtain the signal x naught, which has, so basically when we have decimation first, it will select every decayth decayth entry of xn, and that is what z2n will be. So when we pass x of n through a decimator which has d is equal to dk, what happens is that after it selects the first entry, the other entry it will select is xdk. Then the third entry it select will be x of 2dk, right? Because d is equal to small dk. And that this is the signal that we will get, z2n. Now we have to pass it through an interpolator, and when we pass it through an interpolator, there will be some zeros added between two sequences, and the number of zeros will be such that if, two sequences will be displaced by ik. So that means that we will have to add ik minus one number of zeros, because then xdk will be present at ikth position or ikth time index. So, and because that is what I is equal to ik. So this is what happens when we look at decimation first, and this is what y2 will be. Now, if we take the case when interpolation is first, so first of all, we'll obtain Z1n, which is nothing but the original xn sequence with zeros. Now, the number of zeros will be ik minus 1 because I is equal to small ik. So, ik minus 1 number of zeros have to be added. And when I pass it through a decimator, what happens is that it will select now every dkth element. So if it selects first some element x naught, then whatever element gets selected next, xd. Now xd could be anything, but there has to be a gap of d minus 1, right? So basically the number of zeros has reduced to d minus 1. And the next element will be at simply at dk. So now we can compare y2n and y1n, and we can see that these two are same when this x decay. So this is xd. So after x naught, we get a non-zero value at xd in y1, and in y2 we have a non-zero value at xdk index. So these two indexes must be same, or d should be equal to dk for y1n and y2n to be the same. And from here we can say that k is equal to 1. So these two sequences are same only when k is equal to 1, or in other words, these two sequences are same only when d and I are relatively prime. So this is the proof of this part. So is it clear? Did everybody follow?
Yes, sir.
Yes.
Okay. So this was simply one question where we saw how interpolators and decimators, using interpolators and decimators, we can get different kinds of sequences. Now let's look at, well, this is the last question, question number 3. It has two parts. So the first part is something that we have already seen before. So the first part is something that we've already seen, and here we have the signal x of n. There are these three filters, H0Z, H1Z, and H2Z, followed by a downsampler of 3, right? So recall from what you have studied in the polyphase decomposition lecture, these are nothing but decompositions of some filter Hz with, and there are 3 such decompositions. So the question says that consider the system shown in the figure above. Assume that H0, H1, and H2 are given as follows. So H0 is this filter whose value is 1 for mod omega less than pi by 3. Similarly, we have H1 e raised to the power j omega, which has a which has a bandwidth of pi by 3 again. So it is from pi by 3 to 2 pi by 3. And similarly, we have H2 e raised to the power j omega, which varies from 2 pi by 3 to pi. And it is asked from us if we can reconstruct x of n from y0 n, y1n, and y2n. So again, looking at the diagram, these are the 3 symbols y0, y1, and y2, and we are supposed to compute x of n back from these 3 samples, these 3 subsequences, right? So before we look at the second part, let's just try to solve this particular case. So if you, for this question, solution is like this. So y0 n, y1 n, and y2n are nothing but subsequences of x of n. So we have made these 3 subsequences of x of n because now we have a filter which is in a polyphase decomposition, which has a polyphase decomposition with number of phases is equal to 3. So we have m equals to 3, and that is why we had 3 filters in the original diagram, and we obtain these 3 signals y0 n, y1 n, and y2n after passing them passing x of n through those 3 decomposed filters. Now it is asked from us that we have to again get back x of n. So the first thing that we notice that all the three filters have a bandwidth of 2 pi by 3, which means that there will be no aliasing introduced by downsampling. So because the overall frequency from minus pi to pi is uh, basically the filters cover some part of the overall frequency, and there is no aliasing between any two filters output, right? And aliasing is not there uh, the downsampling is of 3, and we have h naught z, which has a bandwidth of 2 pi by 3. So the band basically the frequency upper bound is less than this value. So that is why there will be no aliasing. And now we can reconstruct x of n simply in the same manner as we did for the impulse response. We have these signals, we will pass them through the upsamplers with the same I is equal to d, and then we can pass them through these three filters. These filters have a amplitude scaling of 3, and this amplitude scaling of 3 is introduced so that because the if you look at the frequency spectrum after passing them through the downsampler, its magnitude becomes 1 by 3. So to compensate for that, we have these factor of 3, and we can add these three signals again to get x of n. So this is in the same manner as that which was done in the polyphase decomposition lecture for h of n. Instead of h of n, here we have some other sequence x of n for which we are doing this. So this is how we can reconstruct x of n. Now let's look at the second part, which is a little bit more interesting. Here we are given this again this sequence x of n, and we have these two signals, two filters h3 and h4, and we have been given their Fourier transforms. So h3 has e raised to the power j omega is equal to 1, so its DFT is basically 1, and for h4 e raised to the power j omega, its magnitude is equal to 1 from 0 to pi, and for omega from minus pi to 0, the magnitude is minus 1. And then they are passed through these two downsamplers of magnitude 2. That gives us y3n and y4n. Now again, it is asked from us if we can reconstruct x of n from these two y3 and y4n signals. So from these signals, we have to again obtain x of n. So here, this h3 is simply 1. So if we follow the same approach that we have been following in polyphase decomposition, that we after when the signal passes through some filter and some downsampler, we pass it through an upsampler and the same filter to obtain some figure, to obtain some other sequence, and then we add them together to get the signal again. So that is what we have to see if that approach will work here as well. So let us look at the solution. So I have done the same thing here. I have taken x of h of sorry, I have taken x of n. Uh, Up to this point, we have been given in the question that it is passed through h3 and also h4. There is downsampling of 2, and I have named these signals as w, y, and v. Now, after downsampling, we pass it through an upsampler as well, and similarly, this signal after downsampling is passed through upsampler and h4z. Here we don't need any other filter at this location because h3z is simply 1. I mean the DFT of h3 is 1. So this is the arrangement. Now we have to see whether on adding these two signals v3n and sn, whether we can get x of n back or not. Okay, so so we use this denotion, these two notations, xen for the even samples of the signal x of n, and xon as the odd samples of x of n. right? So that means that whenever we are talking, whenever we are saying xen, it means that it is nothing but x of n, but for even n, and for odd values it is simply 0. Similarly, x o n is nothing but all the odd values of x of n, or all the values of x of n at odd time indices, and it is 0 at the even indices. Okay, so we will try to write down what each of these sequences is, and then we see, and then to see that summing up these two, whether it gives us x of n back or not. So first of all, let's start with the this first part of w3n, y3n, and v3n. So v3n is nothing but, or let's say first of all, look at what y3n is. Y3n is nothing but w3 2n, because it is being passed through downsampler of 2, so its time period will change. So that is nothing but w3 2n, and w3 2n is nothing but x 2n, because h3 is 1. So we can say that y3n is x of 2n. So we have written here that y3n is nothing but x of 2n, right? So we can look at it like this, that if x of n was this sequence of x0, x1, and xn, when y3n, which is x of 2n, is nothing but every alternate value in that sequence. Similarly, if we look at v3n, so v3n is after we pass it through this upsampler, so which means that there will be a 0 inserted between every alternate value, because I is equal to 2. So v3n is nothing but y3n with 0 inserted. So this is v3n. So we can write v3n in terms of x of n as it is basically x of n for all the even values. So for the values 0, 2, 4, and so on, it is simply x of n. And for the all the other values, it is 0. So in this way, we have written v3n in terms of x of n. And if you look at this, this basically means that v3n is nothing but xen, the even components of the sequence x of n. So going back to the diagram, v3n is the even components of x of n. Now what remains to show is that if s of n is the odd components of x of n, then we can say that by summing up the odd and even components of x of n, we will get the x of n completely back. So, this signal, if we look at the, if we look down here, so you can see that this is h4z was given to us as this. We have been given the DFT of h4, which is 1 for 0 to pi and -1 for minus pi to 0. Okay, so we can find out its inverse DFT, which will give us the sequence h4n, or the impulse response, which will be equal to -2 by j pi n for odd n, and 0 otherwise. So I leave the calculation to you, but this is what we will get on trying to compute the IDFT of this. Now, once we have gotten this h4n, we have two things to note here. The first is that every other sample of h4n is 0, right? You can see that only the odd samples are there and every other is 0. And the second thing to note is that if I take this product h4 e raised to the power j omega, multiply it with itself, I will get a 1. So that is clear directly, because for 0 to pi it's 1. If I multiply it with 1 again, we will get 1. And for minus pi to 0, it is -1. I multiply it with -1 to get 1. So this thing holds. And if I take IDFT, it means that the impulse response convolution with itself is nothing but delta n. So two things are to be noted from H4n. Now we look at what these sequences will be. what W4n, Y4n, and V4n will be. So V4n is clearly just W4 2n, and similarly, uh, V4n is Y4 of n by 2. So let's look at that more clearly. So first of all, I said that V4n is nothing but W4 of 2n, which means that all the alternate values of W is V4n. Then, uh, sorry, is Y4n. And then we calculate V4n after passing Y4n through the upsampler with a sampling period of 2. So what happens is that it will just give us W4n or even values, and for odd values it will give us 0, because after passing it through upsampler there will be zeros between these values. So it will be W0 0, W2 0, and so on. So I can say that V4n is this, right? Now what is W4n? So W4n is nothing but the convolution of x of n with h4 of n. So uh, here I have written W4 as the convolution of the input signal and the filter, the impulse response of the filter. So I have just replaced this with this here. And because I know that Hn, the signal h of n, only existed at the odd values, it means that when I take this convolution, I will get nothing but x on, which was the odd values of xn, because h of n is only non-zero at the odd values. For the even values it was 0, and using that we get that v4n is nothing but x naught n, x naught n, right? And then finally we can compute this sn. Sn is v4n convolution with h4n. So this should actually be yeah this should have been v4n, which is the convolution of this odd part and its and h4n. And so we get this part, we get this as xon. Okay, this is fine. This is v4n, which is the odd part of x convolution with h4n, and we get the odd part because h4n is nothing but non-zero. H4n is non-zero only at the odd samples. So this is what V4n we will get. And finally, the output, which was S of n, will be the convolution of V4n with H4n, right? So S of n, I will go to the diagram again. S of n is nothing but the convolution of V4n and H4n. So that is this thing. And V4n is nothing but this term. So when I write it here, we get H4n convolution with H4n because one comes from here, right? And we know that this is simply delta of n, which we had originally seen, which we had noted from here. And using this property, we can simply say that S of n, that is the output, will be nothing but the odd entries of x of n. That means that when we finally take the summation, we have the even and odd entries, and that means we will get the whole x of n back, right? Because at the end, we are taking the summation of v3n and s of n. v3n is the even part and s of n is the odd part, which gives us the overall x of n back. So this question was a little bit there were a lot of things involved, but basically what all we are doing is we are doing the polyphase decomposition of this filter, and then we are reconstructing the signal back after passing it through this polyphase decomposition of by when we first obtain these subsequences, we pass them again through this uh, a similar arrangement to get x of n back. And that was this question. So, are there any doubts? Was it clear? Is there anything that was not clear?
It's fine, sir.
Okay. I will suggest that you also take a look at this PDF file. I'll upload it to the classroom. There were a few things that you might have to look at again. So, just to make yourself acquainted with these ideas. And yes, so basically, these two are very important concepts. One is multi-rate sampling, and the other is polyphase decomposition. And most of the things we can do with these, either the two identities that we discussed in the first question, or this arrangement of polyphase decomposition. And we can, when we look at each of these sequences, we can find out basically how we can obtain x of n again. This was the gist of question number 3. So, are there any doubts overall? Because that is the end of tutorial 6.
No,
Okay. Okay, if there are no doubts, then we can end this meeting here. Thank you. You all can leave this meeting now, if no doubts.